Hello everyone, welcome to this first video in a course on topology. Before we get to the content of this video, let me just start by giving you the plan for this course. So my plan for this course is to go over some basic facts about topological spaces and then talk about continuous maps and some compactness theorems, and we might get to the Stone-Weierstrass theorem at the very end of this course. Since I'm planning to cover as many facts and theorems as possible, it might be a good idea to have some slides to go over, and I'll make sure to write down proofs. So I'm gonna be working out the proofs in details instead of just presenting them or reading them. Alright, so let's get started. In this video, what we'll do is we'll introduce the basic terminology and some basic definitions needed to start discussing topology and topological spaces. This video is gonna be like an introductory video. We're going to start from the very beginning. We're going to start by defining what a topological space is. So usually, well, first of all, let me motivate this for you. Why are we doing this? So, usually when we study analysis, when we do real analysis, we usually want some building blocks. We need some notions to start with. And the very basic concepts that we need are limit, convergence, and continuity. So what we observe is that working in Euclidean spaces, working in R to the n, isn't always enough. There are some important facts that we can get in the general sense. If we look at sets more general than just Euclidean spaces, and if we look at things more general than metric spaces, we get to we get some facts that we don't have, or at least we can't see in the basic framework. So what we do is we generalize the framework, and then we look at the general. We look at a broader. We look at broader spaces, broader definitions, and we get some important facts, and we'll see that the fundamental element here, the very basic thing we need to define, is the notion of openness. Once we define what it means for a set to be open, we can get all of these notions of limit, convergence, continuity, and so on and so forth. So our first target is to define what's so-called topological space. So we're gonna start with a set that is non-empty. We're gonna start with a non-empty set X, and we're gonna define a topology on X to be just a collection of subsets of X satisfying some properties. So you can think about it in this way. What we need to do is we need to enforce some properties that open sets in the Euclidean space satisfy. Like, for example, we need to enforce the property that if I take an arbitrary union of open sets, I still get an open set. And we want a finite intersection of open set to still be an open set. So these basic properties, we need this collection of subsets, or this collection of sets that all fall in X to satisfy. And we need in addition that the empty set and X to be in T. So we need the empty set to be in T, X to be in T. We need an arbitrary union of sets in T to still be in T. And we need a finite intersection of sets in T to still be in T. And this is going to be our definition of openness. We're going to define openness. We're going to define open sets to be sets of T. Like every set of T is an open set. Okay, so and a set is open if and only if it's in T. With respect to this topology. So in this case, what we're gonna say U, a subset of X, is open with respect to the topology T on X, if and only if U is in T. All right, and we're gonna say a set is closed in X. We can call it V. V in X is closed if and only if its complement is open, which is the same as saying that its complement falls in T. So we have these very basic definitions that we're making here. We're starting with a collection of subsets of X that satisfy some properties. And what we're gonna do is we're gonna define open sets to be the sets falling in T, and we're gonna define closed sets to be those whose complement is open. In other words, those whose complement is in T. Okay, so I guess now it's time for some examples. So we're gonna go ahead and do that. But before I do that, let me just mention that usually we call the pair X, comma T, we call it a topological space. And when T is understood, we can just, usually you will see that, we'll be like saying something like, let X be a topological space, the topology T, if the topology T is understood. All right, so we're gonna go ahead and see some examples now. We can start with the trivial examples. So there is actually a topology that is called the trivial topology. And guess what we're gonna do? We're gonna just take a collection of subsets of X that satisfy one, and the rest of the conditions will follow easily. So this topology contains only the empty set and X. So this is a topology on X, on a set X that is non-empty, and it is defined by this collection of sets. And of course, these sets are in X. These are subsets of X. T contains the empty set and X. Any union of sets in T is still in T, and any finite intersection of sets in T is still in T. So guess what? This is a topology on X. And if you wonder what are the open sets here, well, it's easy to observe that the only open sets here are the empty set and X. And what are the closed sets? These are also only the empty set and X, because these are the only thing whose complement is in T, right? Okay, so let's look at the second example, which is the discrete topology. So these names are important, and it's important to remember them. So please make sure that you familiarize yourself with these terms. So the second example we're going to look at is the discrete topology. And what we're going to do here is like, we're going to just do it like, we're going to take all the subsets of X and we're going to put them in this collection of sets. So in other words, we're going to take the power set of X to be the topology. So so here another topology on X can be defined as the collection of all subsets of X. In other words, what we're doing here is we're declaring every subset of X to be an open set, right? So we're saying, give me any open set, give me any subset of X. I'm gonna say this is an open set, okay? And by doing so, we immediately have every every subset of X is also closed because its complement is a subset of X, and hence it's open, and hence the original set is closed. So for example, this is a topology because clearly the empty set and X are subset of X, are subsets of X, and hence they both belong to T. And clearly, if I begin with any collection of subsets of X, if I begin with any collection like UI for some index set I, then their union is definitely their union is still it's still a subset of X, right? So that's clear. So if all of these are subsets of X, then their union is definitely a subset of X, and hence their union also belongs to T. So their union is open too. And if we take like a finite intersection of sets, so if we start with any finite UIs, then if we take their intersection, then that's also trivially an X, because each and every UI is an X, hence their intersection is necessarily an X. So it's a subset of X, so it's in T. So this means T is a topology. Okay. So these are trivial examples. Let's go ahead and see some more involved examples. So let's look at what's so-called the cofinite topology. So we're gonna see that this topology is very important, and but we're gonna postpone discussing its applications or its importance for now. But let us see why this collection of sets is a topology. Okay, so here's what we're gonna do. Say we started with an infinite set, okay? We're gonna start with an infinite set, whatever the set is. We're gonna define T as a collection of subsets of X defined as follows. We're gonna declare U in T if and only if U is empty or the complement of U is finite, okay? And hence the name cofinite. So it looks like it's a dumb definition now, and it doesn't look like it has any significance, but we'll see some important applications later. But let us now see why this thing is a topology. So let's see. For example, let's go over the stuff quickly. So does it contain the empty set and the whole set? Well, of course it does, because if I take the empty set is clearly in T by definition from here, and X is also in T, and this is because if I look at X minus X, this is the empty set, which is finite. So this forces X to be in T by this criterion here. So let's see, is the union of any, is like any arbitrary union of sets still in T? Like if we start with an arbitrary union of sets that are in T, is their union still in T? Let's see. Well, if we take their union, so what we're gonna do is we're gonna take the union of the UIs, and we want to show that this is in T. So what we can start by doing is we can take away all those that are not empty. Because if they're empty, then the union is going to still be the same. So let's assume all of these are non-empty. But then necessarily what we have is for every set here is going to satisfy the property that X minus that set is finite, right? So this is something that is necessarily true. Now, if the union is empty, then there's nothing to show, right? If empty, there's nothing to show. It's cleared. It's clearly in T, right? Because it's an empty set. Now, if the union is not empty, meaning there are some sets ui who satisfying x minus ui is finite, then we can clearly see that if I take x minus that union of ui's, then we can clearly see that by definition of this subtraction of sets, we can see that this is the intersection of x with the union of ui's complement, and this is definitely and of course this is definitely x intersected with the intersection of the ui's complement, like this. But this is definitely contained in x intersected with, so here we're assuming that none of these ui's is empty. So x intersected with, for example, u1 complement, because this is cleared, and this is equal to x take away u1 by definition of difference of sets, but this is finite, which is finite. But since this is finite, then definitely this is finite, then definitely the union is in T by this criterion. Okay, so we automatically get that the union of the ui's is in T. Alright, but then there's one thing left to be shown, which is that finite intersections are gonna still be in T. So if we take a finite set of elements in T, and we take their intersection, so let's do that. So if we take their intersection, we want to show that their intersection is still in T, but that's not so hard, that's easy. Of course, we can also take away all these empty sets if we wish. So there are two cases. If empty, then it's clearly, then we're done. Like if all of these sets is empty, then we're done, because the intersection will be the empty set, which is in T. If one of them is not empty, so if some of them is not empty, then we look at this difference, and what we see is, by definition of differences of sets, this is x intersected with the intersection of ui's I equal 1 to n complement, and this is x intersected with the union of ui complement I equal 1 to n, and of course this is the same as the union of I equal 1 to n of x intersected with the ui complement, and this is the same as the union of x take away ui. So each of these what we have is so we're saying here we're gonna assume none of the ui's is empty, otherwise we work with the intersection of the ui's I equal 1 to n such that ui is not empty. In other words, we can since this is gonna be the same as the full intersection, right? So we're gonna assume that none of these ui's is empty, and hence since all of them are in T, then we must have this property. Since this property is not satisfied, then the other property should be satisfied, and hence each and every one of these is a finite set. But a finite union of finite things, a finite union of finite sets is finite. So this is finite. And of course, this gives us automatically that the intersection of the ui's I equal 1 to n is in T. Alright, so this proves that the cofinite collection of sets is actually a topology. And I'd like you also to remember this name because it's an important name, and we'll see how this pops up later. Alright, so let's move on and see some other examples. Some other important examples include the metric topology and the relative topology. So the metric topology is it's usually called the usual topology. So what we do is we start, say we have a metric space. So we have a set X, but it is equipped with a metric space. For example, the Euclidean, for example, are the real numbers with the absolute value, right? So we have a metric space. Suppose we started with a metric space. Can we construct a topology on X? Well, sure we can. And as we'll see later, to construct a topology, it's enough to declare what the open sets are in most of the cases. So here, for example, we automatically get a topology on X if we declare open sets of X to satisfy the property. So if we declare open sets of X as such, so what we can do is we can take T to be the set of U's in X such that for every X in U, let's say there exists some epsilon positive such that the ball of center X radius epsilon is contained in U. So we're gonna declare U open if and only if every point in U contains some ball that is every point of U has some ball around it that is totally contained in U, right? And of course, you see, we automatically get that this is a topology. As a matter of fact, it's enough to take all the open balls with their union to be the definition of T. But this is clearly a topology, and I'll leave it for you as an exercise to show that this is a topology. This is not hard. You just need to show that. Of course, here we need the empty set. It's trivial to see that the empty set and X are in the topology, and of course X isn't the topology because every ball in X is contained in X, right? And for the union, for the arbitrary union, it's also trivial by the definition of union, because if X is in the union, then X is in one of the things I'm unioning. So that's also trivial. And like for the finite intersection, it's also trivial because X is in the intersection if and only if it's in each and every one of the things I'm intersecting. It's going to be also trivial to construct the 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 epsilon that you need. It's going to be the minimum of the epsilons coming from each and every un. So I'll leave it to you to look at this, and we might come back to this later. But let me just talk a little bit about the relative topology, which is the topology with respect to or the topology on a subset of the original set that we started with. So here's what we're gonna do. Suppose we started with a topological space X that is not empty, okay? Then let's take Y to be a subset of X. We ask a question: can we equip Y with a topology? Can we construct, or can we define a topology on Y? And the answer is yes, and we can sort of do it in a trivial way. What we can do is we can define a topology on Y to be the set of all open sets of X intersected with Y. So what we get, what we'll do is, so remember, sort of like trivially one can write T, it's the set of U and X such that U is in T, right? If I'm gonna write it in this in this way. So when we look at when we want a topology on Y, what we can do is we can do something basic, namely we can project the whole thing onto Y, right? So what we can do is take each and every open set of X and just project it, put it in Y, make it or force it to be a subset of Y. And by doing so, I claim we get a topology on Y. Well, do we need to spend time showing this? So if you observe here, the empty set intersected with Y and X intersected with Y are elements of this topology, because the empty set and X are open sets in X, are like elements of T. But this is the empty set and this is just Y. So this means the empty set and Y are gonna be in TY. And this is the first thing we need to show when we claim something is a topology on Y, right? And if we take any arbitrary union of elements that are in TY, then they're gonna look like this, right? They're gonna look like this. It's an intersection of UI intersected with Y for every where the elements UIs are gonna come from T, are gonna be open sets of X. But this is of course the same as the union of the UIs intersected with Y. But you know, this thing is a union of elements of T. So since T is a topology, then this is necessarily in T, but then necessarily this whole thing, by definition of Ty, is gonna be in Ty. And thirdly, if we start with any intersection, any finite intersection of elements of this topology, Ty, then this intersection is gonna also be the intersection of Yi intersected with Y, like this. And by definition of T, since T is a topology, then finite intersections of elements that are in T are gonna be is gonna be in T, right? So this makes this whole thing in Ty, by definition of Ty. All right. So we have this relative topology or subspace topology. So for every subset, I can define a relative topology on it by just projecting the whole, like projecting each and every open set of the big space onto the smaller space. Okay. One important thing I want to mention about this topology is like I want to give some examples of openness and closedness. So let me just go over quick examples here. So let's say, first of all, let me define what openness and closedness here. So we're gonna say, we're gonna use this definition here. We're gonna say that a set, let's call it A, is relatively closed, let's say relatively open or closed in Y if so if we start with a set that is in Y, we're gonna say that this set is relatively open with respect to the topology on Y, or the relative topology on Y, if there exists an open set respectively closed set, let's call it U in X, such that A is equal to U intersected with Y. So let me just restate what I'm saying here. We're gonna say a set A in Y. So we have this big space X, and we have a subspace Y. We're defining a topology on X. So on this we have a topology T, and on this we have a topology Ty, and we're gonna say a subset, let's call it U, a subset U of T is open if it's an intersection of an open set of X with excuse me, we called it A, so this is A. So A is open in Y if it's the intersection of an open set in X with Y, and it's closed if it's the intersection of a closed set in X with Y. In other words, we're gonna say A is open in Y if it's the projection of an open set onto Y, and if it's we're gonna say it's closed if it is, like, quote unquote, the projection of a closed set in X to Y, right? So I don't know, you might be any set of X whose intersection is gonna be, for example, let's say trivially, for example, that U is the union of these two things, for example. Then the intersection of U with Y is gonna be this A, and U is originally open in X with respect to the topology T. In other words, U is gonna be an element of T, right? And we're gonna say A is an element of T sub Y if and only if A is the intersection of an element of T, which is U, with an element with Y itself, right? With Y. Okay, cool. In other words, the only open sets of Y, or the only open sets in Y with respect to the relative topology, are gonna be of this form, where U comes from T. In other words, U is an open set of T. of X. All right. So let me just give some important remarks here about this thing. So one important thing I want to mention is, let me give some example because it can be hard to imagine these if you're doing it for the first time. Let's suppose we're starting with the real numbers, and we're using the usual topology. We're using like we're defining open sets in the usual sense, and in this sense, right? We're defining open sets in this sense. Let's take y to be, for example, 0, 2. Okay, let's take it to be this set 0, 2. Notice y is open here. Okay, now it's open in X. Okay, so let's see. Since y is a subset of X, then and X has a topology on it, defined in this metric topology way, then what we're gonna do is let's look at some examples of sets that are relatively closed, for example, or relatively open. So let's look at an example of a relatively closed set. So for example, if you look at C equals to, let's say, 1, 2, okay? I claim that this set, which is of course a subset of y, you would think that this set is not closed, but it is in fact closed, and I'm gonna show you why. So if you look at let's say the set F, let's call it F, and let's define F to be from 1 to infinity. This set is closed in X. Why is it closed in X? Because its complement is open, right? Because the complement of F is just minus infinity 1, and this is open, right? So this set is closed in X, and C is equal to F intersected with Y. That's obvious, right? This is 1, 2. This is 1 infinity, and this is 0, 2. If you intersect these two sets, you get C, and this is a closed set in X that I'm projecting to Y, and I'm getting this set. Hence this set C is closed in Y. In other words, this set C is closed in the relative topology on Y. Okay, and we call it relatively closed. All right, let's take an example of a relatively open set. Well, a relatively open set can be, you can take a simple example, like you can take U to be 0, 1, for example. If you take U to be 0, 1, then of course this is relatively open, because if you look at U can be written as, I don't know, you can write something like 0, 1 intersected with, this is kind of a simple example here, 0, 1 intersected with Y, which is 0, 2. This is trivial, right? Because 0, 1 is a subset of 0, 2. And this thing, this is open in X. So with the definition of openness we have on X, this is open in X, right? This is an interval that is open in X. And of course it is, it can be written as a set that is open in X, which is this thing, intersected with Y, which is 0, 2. and hence this thing is relatively open in Y. Okay. I'll leave it to you to play with these notions, but yeah, this notion of relative openness and closedness is very important, and the relative topology is very important, as we will see in the coming videos.